You're watching a Channel 98 NBISD TV production.
Hey, welcome to another fantastic edition of Deja Vu. It's Algebra 2. As always, I'm Kevin Corpy, your host for this adventure. Now, today we're going to be talking about polynomials. We've been talking about linear equations. We've been talking about quadratics. Those are actually members of a larger family of functions called polynomials. So today we're going to learn exactly what a polynomial is, look at different types of polynomials, and then we're going to do a few things with polynomials. So you're going to want to stick around. Download the worksheets that I prepared for you from the district website, www.newbraunfels.txed.net, and we'll get going. Lesson 14 already. Polynomials. We're going to be adding, subtracting, and multiplying them today. Now, you're probably wondering what a polynomial is. Well, polynomial is composed of two words, poly, meaning many, and nomial, which literally translates to name. But we're going to take it to mean terms. So polynomial for you at home in math class means many terms. Now, what do these terms look like? Well, it's going to be an expression, not like gee whiz expression, but an expression of terms that contain numbers, variables, and they're going to be separated by addition and subtraction signs. So that's very important to understand from the onset here. Terms are separated by plus or minus signs. So let's look at what makes a polynomial as opposed to another expression. Polynomials must have variables that have non-negative integer exponents. So what does that mean? That means that it could be 0, it could be 1, 2, 3, 4, 5, but it can't be like a negative exponent, or it can't be a fractional exponent like 1/2 or 2.5. As long as we have non-negative integer exponents and we have a combination of terms, we have a polynomial. So this is an example of a polynomial expression. We have a 4 times x to the 5th, that's one term. There's a minus, so here's the next term, 7x to the 3rd plus 2/3. It's okay to have coefficients that are fractions because it's x squared, that's an integer, minus the square root of 3. Well, the square root of 3 is the number in front of an x that's actually missing there. If you want to write it, that'd be x to the 0 because it's not there. 0 is non-negative and it's an integer. So there you go. Now let's kind of look at the anatomy of this little expression right here, because there's several terms that go along with polynomials. First one being the degree. The degree is sometimes called the order, but we're going to use degree. The degree of a polynomial is simply the largest exponent in the polynomial. So if we look through here, we got a 5, a 3, a 2, and essentially a 0, which is really a 1. So the degree of this polynomial would be 5. Okay, so the degree of this particular one is 5. The coefficients, I might have already slipped that word out. The coefficients are pretty much scalar multiples. They are the numbers that are being multiplied by the variables, the numbers in front of them. So on this term, x is the variable, 4 is the coefficient. In this term, x is the variable, negative 7 is the coefficient, 2/3 the coefficient of the squared term, and negative square root of 3 is the coefficient of the x to the 0 term, but because we don't typically write the x, we'll call that the constant. Okay? So the number without an x is a constant. Now the leading coefficient, this is very important. The leading coefficient is not necessarily the number that's out in front of the expression, like a lead dog. That's what makes a lead dog, it's in front. But the leading coefficient for a polynomial is the coefficient that is associated with the variable with the largest exponent. So on the term that dominates, that gives it its degree. And in this case, since we said 5 was the degree, this whole thing is the leading term, and 4 would be the leading coefficient. But you have to be careful because these are separated by addition and subtraction. And we can write these things by the commutative property of addition in any order we want. And so we have to carefully look at each term and make sure we've identified the term with the largest degree. Don't always expect it to be the one out in front, okay? But the one that's associated with the largest degree is the leading coefficient. So now that we have these polynomials, what do we want to do with them? Well, like any good collection of things, we want to start classifying them, pigeonholing them, putting them in little groups. And there's two ways we could do that with polynomials that make sense. The first way is to classify them by their number of terms, okay? And we're going to have names for them. So the first name is going to be a monomial, and a monomial is a type of polynomial, but as the name mono, like monocle, implies, it's going to have one term, a single term. For example, 4x is a single term. It's a polynomial, degree 1. Negative 7 is a polynomial. It's a monomial. It's a constant. Or x squared, the ones like we've been dealing with. So that's a monomial, single term. There's no plus or minus signs there connecting it to another term. Now if we have two terms, binomial like bicycle, that's two terms. So 4x minus 1. There's the minus sign separating the two terms. 4 would be the leading coefficient. X squared plus 2. There's two terms. 2 would be the degree. 1 would be the leading coefficient. Trinomial like tricycle. 3 wheels, 3 terms. We can have something like x squared plus 2x minus 1. This is written in descending order of degrees. So 2 would be the degree and 1 is the leading coefficient. But 1, 2, 3 terms. Or something like this, 4x to the 5th plus 2x cubed minus 3x. There's 3 terms. This one has degree 5 and the leading coefficient is 4. Now once we get beyond trinomials, we get 4 terms, 5 terms. There's really no special names for that. We just call them polynomials. Poly, remember, means many. So we'll use polynomial for anything that has 4 or more terms. We could say a 4-term polynomial, a 10-term polynomial, whatever. So in this case down here, let's look at it. We've got, let's count them. We got 1, 2, 3, 4, 5 terms. So it's a 5-term polynomial. And what is the degree? Well, let's see. The degree is going to be the largest exponent, which it's 8 right there. So since this is the term with the largest degree, that is the leading term. Now it's leading from the rear here. Notice it's not written out front. So the leading coefficient is -9. So be careful again the way that it's ordered. Okay, we can also classify polynomials by their degree. And here's what we're going to do. We have names for each of these degrees. So if we start with a constant, that is it has no x at all, we say it's degree 0. And you saw that on the previous page. I went x to the 0. No x at all, so that's a constant, like -8, -5, 4, 2/3. It's always going to be a monomial. If I kick it up a degree to degree 1, I have a linear. Those are x to the first. So anything that has an x to the first as its highest exponent is going to be linear. It could be something like -6x or -6x minus 2. Okay, at most it could be 2 terms, but it could also be a monomial. Then we kick it up to a quadratic like we've been studying. That's going to be where the highest degree is x squared, and that's going to be at most a trinomial. But it could be anything less than x squared for the other terms. We do have to have the x squared. So for instance, 3x squared plus 2x, or 3x squared plus 2x minus 5. That would be a quadratic. Cubic, now, this is going to be on unfamiliar territory. We're kind of getting into something you haven't seen. A cubic would be a polynomial whose largest exponent is 3. So that would be something like x cubed or x cubed plus any combination of exponents smaller than 3. Then we go up to quartic. That would be an x to the 4 is the highest exponent. A quintic would be highest exponent of 5. And then after that, of course, there's degree 6, degree 7, but we just call those higher degree polynomials. We have the special names up to degree 5 because that's typically what you're going to be encountering in Algebra 2 and maybe even on into pre-calc. Okay, so now that we've got all these polynomials classified, what can we do with them? Well, we're going to start easy with some operations. We're going to add some, we're going to subtract some, working our way up to multiplying. So, how do we add and subtract? Well, it's very important that we add and subtract like terms. What are like terms? Like terms, by definition, are going to be the terms with the exact same variables. Like, I can add an x squared term to an x squared term, but I cannot add an x squared term to an x term, let's say, or a constant to an x cubed term. But I can add constants to constants, x cubes to x cubes. Those are like terms. And remember, terms are separated by plus or minus. So let's look at an example. We've got two functions, f of x, which is a cubic polynomial, leading coefficient 4, and g of x, which is a quartic polynomial, leading coefficient of 1. Let's go ahead and add these two together. There's two ways to do it. You could do it horizontally or vertically. So I'm going to go ahead and do it horizontally. So f of x plus g of x. That's the first step. And now we want to go ahead and write these things down. F of x is 4x cubed minus 2x squared minus 5x minus 4. Okay, and I'm going to put in parentheses just so I can block off the polynomial. I'm going to add to that g of x, which is x to the 4th plus 3x squared plus x minus 2. Now what we're going to do is we're going to go through and kind of take inventory. We want to add like terms together. And I would suggest kind of starting with your largest exponent all the way through, which in this case is x to the 4th. There's no other x to the 4th term here, so he's going to stand alone in the front by himself. We're going to write these in decreasing order. If you underline them or cross them out when you're done, that's a good way to assure yourself that you're not going to use them twice. X cubed would be next, down from 4, and we have one x cubed term right there. and it's positive, so it's plus 4x cubed. Now we'll go through and look for an x squared term. There's an x squared term, there's an x squared term. So I have negative 2x squared plus 3x squared. That's really 3 minus 2, or positive 1x squared. All right, and then I'll underline those because I've used them. And now I've got x terms. There's a negative 5x plus 1x. That makes negative 4x's. So if you think of these things as physical objects, it might help you. Okay? Negative 4 minus 2, we know that's negative 6. And that means we've used every term. And so this is the answer. So the sum of two polynomials is another polynomial. In this case, it's going to preserve the fourth degree polynomial. Okay? We just have more terms behind it. Now we can also subtract them. So let's do this. Let's try g of x minus f of x. Okay? Now I'm going to do this one vertically and see if it's easier for you. We're going to start with g of x. Now if you do it vertically, what you're going to want to do is create a placeholder for any value of x or any exponent of x that's not there, so that you can stack your like terms all the way down. So if I'm starting with g of x, that's x to the fourth. The next term is x squared, so there's no x cubed term. So I'm going to put plus 0x cubed, creating a place for it, and then plus 3x squared plus x to the first minus 2. So I'm walking down, 4, 3, 2, 1, constant, 0. Now I'm going to subtract. And what I'm going to do is, as I write f of x, I'm going to place each of f of x's terms underneath the corresponding like terms for g of x. So f of x is up here, it's 4x cubed. That's going to go underneath the placeholder that I put, minus 2x squared, minus 2x squared, minus 5x, minus 4. Now that I have everything stacked, I can do the subtraction. If you want to put a 0 here to round it out, that's fine. Now we're going to subtract, and it's important to subtract each term. It's effectively distributing it through there. So let's see what we get. X to the fourth minus 0 is x to the fourth. 0x cubed minus 4x cubed is going to be negative 4x cubed. 3x squared minus negative is really plus, so I get 5x squared. X minus negative 5x. Woohoo, lots of negatives. So that's really the same as plus. So I get plus 6x, and here we go, we get numbers. Negative 2 minus negative 4. Well, that's really negative 2 plus 4, or 4 minus 2, which is positive 2. And so there we go, we've subtracted them. Both methods work. The vertical one's a little bit easier when you're starting out. But I would encourage you to try and work towards doing it horizontally, because as you encounter these things in later math classes, this is going to be kind of the standard. Okay? But this is a great way to learn how to do it. All right, let's take a real quick break, watch these valuable public service announcements, but don't go away, because we'll be right back. While you're gone, think about this. What did the mathematician say when he saw one person entering the building, but two people coming out of it? The answer when we return.
Yesterday, my friends told me to smoke some weed, and I did. Then today, they said I should try to outrun Tick-Tick, the little lumberyard dog. And I don't think I can. I'm an idiot. I'm doing stupid stuff, and that ain't me.
No! Live above the influence. Above them, above weed.
It's easy to tell if you've had way too many. But what if you've had just one too many? Buzz driving is drunk driving.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. What did the mathematician say when he saw one person go into the building but two people come out? Well, the mathematician said, if exactly one person enters the building, it shall be empty again. Oh, yeah. Love those integers. Back to polynomials. All right, addition, subtraction, takes a little practice, but it's not that hard. Now we're stepping up to multiplication. Multiplication of two polynomials. If we just multiply by a scalar number or by a constant, it's effectively distribution. But when I start multiplying two non-trivial functions together, those with x's or more than one terms, it gets a little interesting. And you probably learned in Algebra 1 that one way to multiply binomials, in this case we do have a binomial, 2x squared plus 2, times another binomial, x minus 4. This one's degree 2, this is linear. You can use FOIL. Now, I'm not a big fan of FOIL, and that's because it's a singular crutch that you use in the case of the product of two binomials, but there's a more general method for doing it. FOIL is multiply your firsts, multiply your outers, multiply your inners, and multiply your last, and get your answer. You can also do like a Punnett square multiplication, which works nicely. But again, you're in Algebra 2 now, and you want to kind of start taking your game to the next level. So let's try and learn another way to do it. And it's just a very systematic process of multiplication through the ranks, or distributing, okay? So here's what we're going to do. If you're multiplying two binomials together, you can start with the first term and essentially distribute it to all the other terms, in this case both of them, in the other factor. And let's see what we get. 2x squared times x. Well, x times x gives us another x. So if we had 2 and one more, that makes it 2x cubed. When the bases are the same, we essentially add the exponent. So 2 plus 1 is 3. Now we move to the next term. 2x squared times negative 4. Well, now I can get negative 8. That's multiplying the numbers together. And I still have x squared. We're through with this first term. 2x squared's job is done. So now we move down its line to 2, which is right here. And guess what? We repeat the process. We just distribute it to all the terms, in this case both in the other factor. Plus 2 times x is plus 2x. And then 2 times negative 4 is minus 8. And once you have that, then you want to collect or combine like terms, if you have any. Okay, so after you expand, is essentially what we did right here, which is a more general method rather than FOIL, collect like terms. So I have a cubic, I have a quadratic, I have a linear, and a constant. Nothing there is common. It's written in decreasing order. So we're essentially done there. All right? Now, here's a nice little example that I put some words to just to kind of give multiplication some meaning. Now, put on your thinking cap here. Stay with me. If we let n of x equal 2x minus 4, a linear binomial, be the number of magic math pills that's produced by a company at an average cost of a of x, being a cubic, dollars per pill. Okay, so the number of pills produced, a is the average cost it takes to produce per pill. We want to create a function, call it c of x, for how much money has been spent on producing these pills as a function of time x. Well, let's think about that. If I take the number of pills that's been produced and I multiply it by the average cost per pill, which is going to be dollars per pill, notice what's going to happen. The pill units will divide out and we're left with dollars, which is what we want. So in this case, we're going to multiply. So the general template would be c of x equals n of x times c of x, just like that. And now we can carefully plug in the actual equations. So let's see what we get. N of x is 2x minus 4. C of x is negative 3x cubed minus 5x squared plus x. And I deliberately made this now a trinomial. So FOIL does not work, okay? But the systematic process of expanding or distributing does. So let's go ahead and do it. I'll take 2x and I'll multiply by each of the three terms all the way through. So that becomes negative 6x to the fourth. And multiply it times the next one. You get negative 10x cubed. And then 2x times the last one gives you plus 2x squared. So you've taken the 2x and you've distributed it to all three to get this. Now you move on to the negative 4. Negative 4 times negative 3x cubed is positive 12x cubed. Then you get plus 20x squared. And then minus 4x. So you should have 6 terms here. And we do. Now what we'll do is we'll go through, the hard part's done, and combine like terms. Negative 6x to the fourth stands alone in the front. Leading term, leading coefficient, negative 6. I do have a couple of cube terms here, though. 12x cubes, take away 10x cubes. These are physical objects, x cubes I'm holding. I have 12, you take 10 away. That leaves me with 2x cubes. Then the x squareds. I've got 20 plus 2. That's 22x squareds. And then finally, I've got minus 4x. No constant at the end there. So this right here is a pretty nice function now. It allows us to find what the total cost of producing these imaginary magic math pills, there's no such thing, as a function of time x. But I can look at the individual functions individually if I want. So here's the context where multiplication of polynomials actually has some meaning in the real world. All right, so multiplying polynomials is pretty important. But what if we have a single binomial, like a 2x plus 1 or 4x squared plus 8x, and I want to raise it to a higher power? Is there an efficient way to do that? Well, there's a couple of ways. It's called binomial expansion if you start with a binomial. You could do trinomial expansion if you want. or any terms expanded to a higher power, but it just gets more labor intensive. Okay? So here's what we're going to start with. We have 2x minus 1 quantity cubed. Okay? So what that actually means, remember, is an exponent says that we just have 3 of these factors multiplied together, and there's going to be 3 of them. Okay? So how can we do this? Well, one method is to actually start by multiplying any 2 of them together and let the third guy go along for the ride. So if I do this, I'm going to get a 2x times 2x, that's 4x squared. I'm going to pick up a negative 2x on the inside and a negative 2x on the outside. I'm going to get a negative 4x, and then I'm going to get a negative 1 times a negative 1, which is a plus 1. So squaring binomials is something hopefully that you've done already. But if not, you can always use FOIL or do the expansion method we just talked about. Now that's one of the factors. We still have this 2x minus 1 over here that we need to get involved. Okay, so now what we'll do is we'll do our little systematic expansion. I'll take the 4x squared and distribute it to both of these. So I carefully do it, and I get 8x cubed minus 4x squared. That takes it to both. The next term is negative 4x, same thing. Negative 8x squared plus 4x, and then finally moving down to the plus 1 times both of those, that's plus 2x minus 1. And now I will collect like terms, and let's see, I got an 8x cubed in the front, and I've got a negative 12x squared, and then a plus 6x and a minus 1. So there you go. All right? So one method is to write them side by side and just hit it with a sledgehammer. Just actually do the math, get in there. But notice that each line is an equivalent statement to the one above. So I'm working straight down. I don't really want to go off to the side and do that and then bring it back in. Always just bring the other guy down until it's his turn. That's good math.
Deja review.
All right, what's the other way to do it? Well, the other way to do it is really, really cool. It's by use of something called Pascal's triangle, named after Blaise Pascal. Blaise Pascal, if you want to research him, he's one of my favorite mathematicians of all time. He was a theologian, he was a philosopher, he was an inventor. Of course, he was a brilliant mathematician, and he made many lasting contributions. He invented the barometer, which is why the Pascal, the PA, the atmospheric unit, is named after him. He built the first adding machine, which is a very complex calculator, and that's why the computer program language of Pascal is named after him. But anyway, fascinating guy. He actually took this triangle that the ancient Chinese were using, and he discovered some patterns. So how can we use it for binomial expansion? It has many uses, by the way. Anything that's written in the form a plus b, a binomial raised to the nth power, we can find their coefficients by an efficient method. So here's what Pascal's triangle is. It starts with a triangle of ones. 1, 1, 1. And it's going to take ones all the way down the side. And what you do to create the numbers in the triangle is you add the units above. So if I add 1 plus 1, right here I get the 2. And this 1 goes down. So I end up with a 1, 1, 1, and then 1, 2, 1. Well, if I keep bringing 1s down, I can keep that process. 1 plus 2 is 3. 2 plus 1 is 3. 1s come down. So I end up with 1, 3, 3, 1. And it's kind of fun to create. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And you can keep going all the way down and create this great Pascal's triangle. Now for binomial expansion, the top row corresponds with n equals 0, an expansion to the 0th power. This is n equals 1. This is n equals 2. Squaring it, this is n equals 3. And this row right here, the 1, 4, 6, 4, 1 row, corresponds to something to the 4th power. Okay? Now here's kind of a real brief glimpse of the pattern. For instance, if I want to know what a plus b to the 0 is, well, I know n is 0. So it's going to be 1, a coefficient of 1. And that's the only term it is, all right? Anything to the 0 power is 1. If I want to do a plus b to the first, well, we know that anything to the first is itself, so that's just a plus b. But notice that it's 1, 1. Those are the coefficients from the triangle. If I wanted to square a binomial, we just did that. You square the first, you multiply and double, and you square the last. So you get the 1, 2, 1 combination on the coefficients, which is the next row. And that process continues down. If you're cubing it, you have your 1, 3, 3, 1. And if you're raising it to the 4th power, you have your 1, 4, 6, 4, 1 from the triangle. So it's a real nice way to expand something without having to use that big giant sledgehammer. It takes a little bit of practice, though. Let me show you one example. All right, let's say we want to expand x minus 2 to the 4th. I don't want to have to write it out 4 times. It's going to take a while. So here's what I do. I know it's to the 4th, so I write out my coefficients from Pascal's triangle, which are 1, 4, 6, 4, 1. Okay? Ooh, there we are. 1, 4, 6, 4, 1. That's on the row where n equals 4. So here's what I'm going to do. I'm going to write them down here. 1, and I'm going to leave a lot of space. 4, 6, 4, and 1. Okay? Now what we do that we have our coefficients is we're going to write our variables. I have an x and a negative 2. So I'm going to write an x all the way through, x, 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 x. And I'm going to write a negative 2 all the way through. And I'm going to put it in parentheses. Negative 2, negative 2, negative 2, negative 2, negative 2. So each term gets one of the factors. Now the exponents on those terms are what's interesting. So if I start with x and I raise it to the 4th power, I got x to the 4th. All I have to do now is walk all the way down. X to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and x to the 0. And then I go the other direction with the other factor, in this case negative 2. So if I start with 0 here, I get 0, 1, 2, 3, 4. Notice the sum of the exponents in each case is 4. 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3. And now, if I put plus signs in between them all I have to do is go through and simplify, which is a little bit of work, but it's a lot better than expanding it. So here we go. Anything to the 0 power is 1. So I just have x to the 4th. This is going to be a negative 2 times 4, which is actually negative 8x cubed. This is a negative 2 squared, which is 4, times 6 is positive 24x squared. Negative 2 cubed is negative 8 times 4 is negative 32x. And I have negative 2 to the 4th, which is going to be 16 times 1. So plus 16, and remember x to the 0 is 1. Whoa! There you go. There is the expansion for x minus 2 to the 4th. Now if you practice using Pascal's triangle, it's a very, very useful tool, and it has many diverse applications. You can actually find the coefficient for an expansion that's many, many numbers down the line without having to expand the whole thing. And it has a lot of implications in theoretical probability, which Blaise Pascal practically single-handedly invented, okay? Made lasting contributions. So check out Pascal's triangle. Practice it. All right, that's another edition of Deja Vu with Algebra 2. It seems like it came and went so quickly, right? Well, I hope you learned a lot today about polynomials. You can see that there's lots of different terms in polynomials. Pascal's triangle is fun if you get to take a chance to look at that more in depth. But we'll be looking at polynomials again on subsequent shows, which I hope you will join me on. So until then, I'm Kevin Corpy reminding you, of course, to do your homework.